Welcome to UGC lecture series Linear Integrated Circuits. Today we are going to discuss about DC and AC characteristics of operational amplifier. The DC characteristics of operational amplifier are otherwise called as non-ideal characteristics of operational amplifier or input bias current, input offset voltage and thermal drift. And why it is called as non-ideal characteristics of operational amplifier is because the current, we have assumed two parameters before analyzing the circuits. One is the resistance, input resistance is infinite, and so the current drawn by the two terminals are equal or 0. And other one is the open loop voltage gain is high and infinite, and so the difference between the two input voltages is equal to 0. But these are ideal characteristics, but practically the current drawn by the two input terminals is not equal to 0, and because of the imbalances produced in the circuit or non-identical transistors used in the circuit, we will be having some output voltage even the input voltage is 0, and the factors which are reasons for the output voltage if the input voltage is 0 are these DC characteristics, or you can say the input bias current, input offset voltage and thermal drift. And what is this thermal drift is the voltage at the output is not constant for all the temperature. So, it will be again changing according to the change in the temperature. So, we have to consider all these factors and we have to make the output voltage 0 for the input voltages equal to 0 by doing some compensation techniques. So, we are going to see one by one in the DC characteristics. So, first is the input bias current. The input bias current is the average of the current drawn by the two terminals, positive and negative terminal, which is given as IB plus IB minus divided by 2. IB plus is the current drawn by the positive terminal and IB minus is the current drawn by the negative terminal. The average is the input bias current, which is given as the specification for 741. If the 741 is integrated with the help of the FET, it is 50 picoamps, and if it is modeled by the BJT, it is 500 nanoamps. This is the input bias current specification of IC 741. So, with this nanoamps or picoamps, then what is the output voltage if the input voltage is equal to 0, which is given as output voltage is IB minus into RF. So, here, so this is the symbol of 741. IB minus is the current drawn by the negative terminal, IB plus is the current drawn by the positive terminal. If we give the input voltage Vi, but it is set to 0, what happens at the output, which is given as this input, the resistance RF will give some voltage at the output. So, through the bias current IB minus, we will be having some voltage across the resistance RF, which will be seen at the output and which is given as IB minus into RF. So, if the resistance RF is made small, then the voltage will be, the output voltage due to the bias current will be again small, but we cannot make this RF small because which is the deciding factor of the gain of the amplifier. The input resistance must be more. We are always assuming the input resistance for an amplifier as 10 kilo ohms. So, if the input resistance is 10 kilo ohms, then the resistance RF is also higher than the input resistance 10 kilo ohm, because RF is always divided by R1 and R1 is the input resistance of the amplifier circuit. So, RF must cannot be made high. So, we cannot go with this as such. So, we have to do some compensation technique to nullify the output voltage produced by the bias current IB minus. So, what we have to do is, here the R compensation resistance is connected at the positive terminal, in between the positive terminal and the negative terminal. If it is not used, then what will be the effect of the output voltages? We know that the bias current is given as 500 nanoamps for the 741 using 500 nanoamps for 741 using BJT, and if we design the resistance RF as 1 meg ohms, then what will be the effect of the output voltage which is taken as 500 millivolts. So, if we assume that the input voltage is in the range of millivolts, then this is not acceptable. If the voltage is equal to 0, then the output voltage must be equal to 0. If we are measuring or if we are amplifying the input voltage in the range of millivolts, then this will also be amplified with the input voltage. So, we are using this R compensation to nullify the output voltage with the input voltage equal to 0. So, R compensation is connected in between the positive terminal and the ground, and so here the voltage V1 is due to the current drawn by the terminal, positive terminal, and which is IB plus. So, IB plus can be given as V1 by R compensation, and here this RF is also having some voltage drop across it due to the current drawn by the negative terminal. So, which is taken as V2, V2 is given as IB minus into RF, and here V1 is given as IB plus into R compensation. So, now according to the assumptions we are already made that VD must be equal to 0 since the open loop voltage gain is infinite. So, we are applying a KVL at this loop from this point to this point, this ground to the output terminal. We will be getting this equation. This is V1. So, from the ground terminal we are applying a KVL. So, this is V1 plus 0 plus V2 minus V0 is equal to 0. So, you have to apply KVL from this node to this node. So, this is the equation when you apply KVL. V0 plus V1 plus 0, here V1 plus 0 plus V2 minus V0. So, here because IB minus is assumed to be flowing through this direction. So, V2 minus V0, because V0 is actually the voltage drop across RF from this direction. So, V2 is reversed with V0. So, if you take V2 here as positive, then minus V0 will be the direction for the output voltage. So, this is the KVL equation for from this ground to the output point. So, from this equation we can see that the output voltage is the difference between the input voltages, that is V2 minus V1, and V2 is the voltage drop across RF by IB minus, and using this R compensation value, R compensation is going to produce this V1. So, using this V1 we can nullify this V2. So, by selecting a proper value of the R compensation, then we can nullify this V2, so that the output voltage will be equal to 0 for 0 input voltage. So, the value of the R compensation is derived as V1, we have seen that V1 is equal to IB plus R compensation. From this IB plus is given as V1 by R compensation. The node A is at voltage minus V1, this is the node A, this is node A, this is minus V1, because this if this the voltage difference between these two voltages points are equal to 0, then the voltage, whatever the voltage present at this node will be the same voltage present at this node. So, these two nodes are virtually equal. So, here the voltage is V1 and minus V1, so that the voltage at this node is also minus V1. So, what is I1? So, if the voltage at this node is minus V1, I1 is represented as V1 by R1. So, this voltage can be taken. So, V1 by R1 is I1. I2 is V2, this voltage, V2 by RF is I2. If the R compensation is used, then the output voltage will be equal to 0. So, this voltage will be the V1 is equal to actually V1 is equal to V2, because in the last equation we have seen that V0 is equal to V2 minus V1. So, if these two voltages are equal, then only the output voltage will be equal to 0. So, we are replacing V1 and V1 is equal to V2 here. So, I2 can be replaced as V1 by RF. Instead of V2 by RF, we are replacing V1 by RF, because we are using the R compensation to nullify the output voltage. So, V0 is equal to V2 minus V2 or V1 minus V1. So, if both the voltages are equal, then the output voltage is 0. So, I2 is replaced as V1 by RF. and we are applying KCL at this node again, KCL at this node A. So, KCL is the sum of currents flowing through the node is equal to the sum of currents flowing away from the node. So, here at this node, what are the currents flowing through towards the node is I1 and I2, and away from the node is IB minus. So, IB minus is equal to I1 plus I2, and replace the equation for I1 and I2. So, I2 is V1 by Rf plus I1 is V1 by R2. So, these are replaced here and simplified, we will be getting the value of R compensation as the parallel combination of R1 and Rf. So, we have for designing the inverting amplifier, we will always be choosing the input resistance R1 as higher value, normally 10 kilo ohms, and Rf is designed from the R1 value and given gain value. So, after which if you know these two values of R1 and Rf, then we can design the R compensation value, which is nothing but the parallel combination of R1 and Rf. So, parallel combination is R1 Rf divided by R1 plus Rf. That is the formula to calculate the R compensation value. If you use this, then the voltage produced by the bias current will be equal to 0. So, the bias current compensation is by using the R compensation resistance between the positive terminal of IC 741 and ground. And the next parameter is input offset current. So, we have used the R compensation. So, the bias current is nullified, the effect of the bias current is nullified, and the input offset current is nothing but the difference between the bias current. We have assumed that in the previous case the bias current IB plus and IB minus are equal since the transistors are identical, but if the transistors are non-identical, then these two currents are not equal. So, because of the inequality between the bias currents, then we will be having some input offset current. By using the input offset current, the output will again, there will be some output value in millivolts range. So, the output voltage is given as V naught is equal to RF IOS. So, V naught is equal to RF IOS. This IOS is input offset current. So, we have nullified the effect produced by the bias current. Now, we are seeing again output voltage for the input voltage 0, and that is because of the input offset current. So, how can you reduce this input offset current? So, we can use a T feedback network. So, if you see the circuit diagram, in the feedback network, feedback path, we have used a T feedback network. Of the output voltage, if the input voltage, input offset current is present is V naught is equal to IOS into RF. Again the RF is the matter. If RF is reduced, if RF is made low, then the output voltage will be again low, but we cannot make the RF low since it is the deciding factor of the gain of the operational amplifier. So, we are having a T feedback network. So, here this T feedback has the larger feedback value, and this dotted line, that is the pi network, will have a lower feedback value. So, whatever may be the application, we can use this feedback network. If it is going to be an amplifier, then you can have a larger feedback network with the T configuration. And if you are definitely using the millivolts range of the input signal, and you need not to, you have to eliminate the output with the respect to the input offset voltage, then you have to use a very low feedback network using a pi configuration. So, this is the good solution for nullifying the input offset voltage with the input voltage is equal to 0. So, these are the equations to calculate the feedback resistance RF and RS. Next is input offset voltage. We have seen two parameters, input bias current, and if the input bias current is present, then the output voltage is actually depends upon the resistive feedback and the input bias current, which is nullified by the R compensation. and next is input offset current. If the bias currents drawn by the two input terminals are not identical, then we will be again having an output voltage for 0 input. So, for this we have to use a T feedback network, and the next one is input offset voltage. Even though these two compensation techniques are used to nullify the output for 0 input, again there will be some output voltage due to the imbalance in the circuit parameters. So, because of that we are getting some output voltage. So, in order to produce the output voltage 0 in that case, after compensating these two parameters, again if you are having an output voltage for 0 input, then in that case if you need to produce output voltage 0 for 0 input, then you have to apply some input offset voltage to nullify the output voltage. So, that is said to be input offset voltage. The voltage is applied at the input terminal to nullify the output voltage. So, this circuit is the signal is given to the non-inverting input terminal, and the below circuit shows that the signal is given to the inverting input terminal, and these two circuits, if the signals are not given, then this is the equivalent, this circuit is the equivalent circuit. So, signals Vi is made equal to 0, here also the input signal is made equal to 0. So, this is the equivalent circuit if Vi is equal to 0 in both these circuits. With the input offset voltage, what is the output voltage obtained? V naught is given as 1 plus Rf by R1 into VOS. VOS is the input voltage we have given to nullify the output voltage. In the operational amplifier itself, we have a facility to give input signal, input voltage as the offset voltage across these two input terminals 1 and 5. Across this two input terminals, we are connecting a 10K potentiometer, and to the fourth pin the wiper is connected. So, these two pins are called as offset null pins. So, first pin and the fifth pin is input offset pin. So, across these two pins, if we connect a 10K potentiometer and a wiper is connected to the fourth pin, and by adjusting the wiper, the voltage, whatever the voltage, the desired voltage is given at the input to make the output voltage 0. So, this is the input offset voltage which is given in the 741 IC. What do you mean by the total output offset voltage, VOT? The total output offset voltage could be either more or less than the offset voltage produced at the output due to the input bias current or the input offset current alone. Because why? Because this VOS is may be positive or negative, also this IB is positive or negative. So, because of these two reasons, this VOT may be more or less than the offset voltage produced by the bias current, and if the bias current is compensated, then the VOT is given as 1 plus Rf by R1 VOS plus Rf IOS, that is, it is added with the input offset current. If it is not inbuilt given, that is the offset pins is not given, then we have to balance the circuit to make the output voltage 0 for input voltage 0. So, this is the inverting amplifier where the signal is given to the negative terminal, and to the positive terminal we are giving a balancing circuit, that is the potentiometer is connected across two power supplies plus V and minus V. The value of the potentiometer is 50K, and a wiper is connected to the positive terminal through the resistor R3 with the 200 kilo ohms. And here this is the input voltage present to the, this is the input offset voltage present to the positive terminal, which is given as VOS is equal to plus or minus. Why this plus or minus is, we doesn't know what is the voltage is adjusted and given at the positive terminal. So, it is plus or minus V, that is the supply voltage, into RF divided by the total. So, this is the offset voltage VOS which is present at this node. So, this is the balancing circuit for the inverting amplifier. Similarly, for non-inverting amplifier, we can use a balancing circuit at the other input terminal, negative terminal. The positive terminal is taken the signal Vi, the negative terminal is taken the balancing circuit with the potentiometer 50K, the same setup 50K, the extreme ends are connected with the power supply positive and negative supplies, and the wiper is connected with the resistor 200 kilo ohms. So, again this voltage, the voltage at this node is going to be the VOS, that is the input offset voltage, which is calculated as plus or minus V or R4 divided by R3 plus R4. This voltage V into R4 divided by R3 and R4. So, this is the offset voltage given at this point, and this is the balancing circuit for the non-inverting amplifier. If the offset pins 1 and 5 is not used, it is not given in some integrated circuits, then we have to externally compensate the output voltage, make the output voltage 0 due to some imbalances present in the circuit by applying input offset voltage at the input pins. If the inverting terminal is used for the signal, then the balancing circuit is given for the positive terminal. Similarly, for the non-inverting amplifier also. The next parameter is thermal drift. So, we have compensated the effects produced by the bias current, offset current and offset voltage. Again, there will be some output voltage because of the temperature. So, if all the compensations are given and the output voltage is nullified at, for example, 25 degrees centigrade, then for 35 degrees centigrade every compensation is not working, and the output, there will be some output voltage for due to the imbalances or because of the bias current or offset current, for any one of the reasons. So, this is because the offset current drift is expressed in nanoamps per degree centigrade. So, if 1 degree centigrade change, then the offset current will be changing by 1 nanoamps. And similarly, for the offset voltage drift is expressed in milliamps per degree centigrade. So, for a change in 1 degree centigrade temperature, then the voltage will be changes in the range of millivolts. So, we have to have a careful PCB layout to keep this op-amp away from the heat source, and forced air cooling technique has to be used to nullify the output voltage even there is a temperature change. AC characteristics of operational amplifier. There are two important parameters in AC characteristics. One is the frequency response, the next one is the slew rate. The frequency response of 741 is given as, which is actually plotted in the Bode plots. There are two Bode plots, which is the gain with respect to the frequency and phase with respect to the frequency. And we know that the open loop gain is infinite and the bandwidth is infinite. Here, for if the signal is DC, the gain is, suppose it is 90 dB, and if the signal is AC, the gain is reduced. Actually, it has to be constant for any signal. If the gain is 90 dB, then for DC signal or AC signal, it has to be constant, but it is not so. For a AC signal, the gain is reduced at the rate of minus 20 dB per decade for a single capacitance. So, what is the reason behind this reducing gain? Look at the circuit, the equivalent circuit of the practical operational amplifier. So, here the input signals are given and the difference between the input signal is Vd, and this is the internal resistance R1, R0 is the output resistance. So, here there is a capacitance at the output, which is actually imagined that there is only one capacitance. Practically, there are several capacitance effects seen by the operational amplifier due to the physical characteristics of the transistor or effect in the operational amplifier, or maybe the construction details present in the operational amplifier. There will be n number of capacitance effect present in the operational amplifier. So, all the capacitance effect are considered as single capacitance, and due to this capacitance the gain is reduced for AC signals. Okay, we will be looking at this AC characteristics again in the next further classes. In this class, the effect of the bias current, offset voltage in operational amplifier and their compensation techniques. and the frequency response we have just started and we will be seeing in the later class. The other 3 parameters are the AC characteristics, the stability of an op-amp and the slew rate. So, some questions to remember what you have learned. What is the bias current? What is the use of the offset null pins in IC 741, and what is the total output offset voltage? And this ideal value of slew rate we will be discussing later. Thank you.